continuing with section 12.2, as I had mentioned previously, I think that our slots and choices method is actually a much easier way of thinking about permutation problems. But you do have to be able to recognize the permutation and the factorial notation and just be able to evaluate them correctly. So, like if I just wrote 9 factorial, you'd have to know that that means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then evaluate it on the calculator, right? Whether by using the factorial button on the calculator or just actually writing out um, the calculation, right? And then you have to recognize that like 6p3 is really 6 times 5 times 4 and write that out, okay? But again, you can use the calculator or just write out the calculation and punch it in, okay? So if we had something like 7p7, if you think about what we said before, what is this really equivalent to, right? We had said that this is a way to think about this is it's 7 objects arranged 7 at a time. Well, if I'm really arranging all 7 objects, right? So this is 7 objects arranged 7 at a time. That means that I would have 7 slots. For the first slot, I'd have 7 choices, then 6 choices, then 5 choices, then 4 choices, then 3 choices, then 2 choices, then 1 choice. So this is actually the same as 7 factorial. So 7p7 is really the same as 7 factorial. And what ends up happening is this still works with our definition, our formal definition of 7p7. 7p7, if you look at our formal definition, would really mean 7 factorial over 7 minus 7 factorial, which is really 7 factorial over, well, 7 minus 7 is 0, right? So this is technically 0 factorial. But what ends up happening is 0 factorial is actually equal to 1, right? And I mean, you can even verify that on the calculator. That's just one of those like weird math things that you kind of have to accept, right? That 0 factorial is 1, right? So when I do 0 factorial, when I do 7 factorial divided by 0 factorial, it's really the same as 7 factorial. Okay, so 7p7 is really the same as 7 factorial. And actually, interestingly, 7p6, even though it's not exactly the same, it would give you the same value, right? Because 7p6, if you think about it, it would be 7 times 6 times 5 times 4 times 3 times 2. So I'm going all the way down to 2, but if I went to 1, it wouldn't change it, right? Because when you multiply by 1, it's not changing anything. So you can verify that, right? So if I did 7 factorial, I get 5040, and if I did 7p6, I'm going to get the same thing. So whether I do 7 factorial or 7p6, it's actually the same answer. So the same thing with like 9 factorial and 9p8, for example. They would be the same. So let's say that, remember we had that last problem about the passwords with the letters and the digits. So if we think about that problem again, but we say repetition of the letters and digits was not allowed, you can still write it out the same way with the slots and choices. So you can still say, all right, I have 2 digits and 2 letters, right? Digit 1, digit 2, letter 1, and letter 2. But now the difference is, so for the first digit, yes, I would have 10 choices. But now for the second digit, I can't repeat whatever I chose. So I'd only have 9 choices for the second digit. And then for the first letter, I'd have 26 choices. But then for the second letter, I wouldn't be able to repeat whichever one I chose. So I'd only have 25 choices. So that's actually going to be 10 times 9 times 26 times 25. And 10 times 9 times 26 times 25 is going to give me 58,500. So there's 58,500. But you could have also written that in our permutation notation, right? Because if you think about it, what is What is 10 times 9 in permutation notation? What is 26 times 25 in permutation notation, right? So 10 times 9 in permutation notation, this was the first two factors of 10 factorial. So this one was 10p2. And what was 26 times 25? It was the first two factors of 26 factorial, which is 26p2. So this was actually 10p2 times 26p2, which should also be 58,500. So again, if we try this on the calculator, I mean, this is kind of silly to do this. It's a lot of typing just for a quick calculation, but just to verify it, if you do 10p2 times 26p2, that looks weird, but this should be correct. 58,500, right? It looks strange the way you have to type it in on the calculator, but it's correct, right? This is just saying 10p2 times 26p2. So you can verify there that you get the same thing. So that's another way of writing that calculation if you wanted to write it in terms of the permutation notation. All right, now switching gears inside section 12.2, we're now going to talk about combinations versus permutations. All right, so when we were doing permutations, we were arranging, right, or ordering. When you switch gears now and talk about combinations, you're no longer arranging, you're basically just choosing a certain number of objects from a larger group, right? So you might have like 8 objects and you're just choosing 3 of them at a time. 5 objects, I'm choosing 2 of them at a time, so on and so forth. So the difference is that order is not important. And really, that's like the most important thing to remember in permutations and combinations, what everybody always stresses. Permutations, order is important. Combinations, order is not important. Okay, so like if I had AB in a permutation, BA would be different, right? AB and BA, if I'm dealing with permutations, they're different. But if I have AB or BA in a combination, order doesn't matter, so they're the same thing. So that's the idea. So what's the definition of a combination? There it is, NCR, right? So if I have n objects and I'm choosing r of them at a time, the formal definition is n factorial over n minus r factorial times r factorial. So if you look at this, the n factorial over the n minus r factorial, that's actually npr, right? So NCR is really npr, but then you also have an additional factor of r factorial in the denominator, all right? So just look real quick at the example that I gave you, right? 7c3 would have been 7 factorial over 7 minus 3 factorial times 3 factorial, which is really 7 factorial over 4 factorial times 3 factorial. Now you're going to look at this and you're going to say, well, Lopez, how did you get from there to there? Well, if you want to see that written out, what it is it's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 3 times 2 times 1. So look what happens here. Everything from 4 down here cancels, and then I'm just left with 7 times 6 times 5 over 3 times 2 times 1. All right, so that's really the way that you're going to want to think of these. You're going to want to think of these as just doing 7p3, which is 7 times 6 times 5, but then dividing by 3 factorial, right? So rather than always show all these steps, if you think about this, think about this as np4, right? I'm sorry, not n, 9p4, right? 9p4, which was 9 times 8 times 7 times 6, that's 9p4, divided by 4 factorial, which is 4 times 3 times 2 times 1. So 9c4 is actually that calculation, right? And again, I'll verify it on the calculator. So if I did 9 times 8 times 7 times 6, oops, calculator's not on. 9 times 8 times 7 times 6. and then I did that answer divided by, but see, now I need parentheses here because I'm dividing by the whole thing. So 4 times 3 times 2 times 1, right? I'm not just dividing by 4, I'm dividing by 4 times 3 times 2 times 1. So that gives me 126. And if I punched it in on the using the combination button, it would be 9 math. I go to PRB button, but now I choose NCR and do 4. So 9C4 is also 126. Okay, so it works out. All right, and as I wrote in that box below there, the easier way to think of NCR is really NPR divided by R factorial, which is what I did up here, right? This was 9P4 divided by 4 factorial, right? So that's really what I did here even, right? This was 9P4 and this was 4 factorial. So if you're doing 8C2, 8C2 is really going to be 8P2 divided by 2 factorial. So it's really just going to be 8 times 7 over 2 times 1. And that's going to be 56 over 2, which is going to be 28. And again, you could do that on the calculator. 8 math NCR2, 28. Right? So it works either way. So again, the most important thing to remember with combinations is you use them when order is not important. So maybe I'm choosing groups of people, right? Like if I break up a class into groups of 4, let's say, order doesn't matter. You don't have any special positions inside those groups. So that would just be a combination. You're choosing toppings for a pizza. Technically it doesn't matter what order I put the toppings on, right? If I'm putting pepperoni and sausage, if I put the pepperoni first or the sausage first, doesn't really matter. So that would be another example of using a combination. So how many distinct 5-person groups can be chosen from a class of 15 students? So in this case, I'm not using all 15 students, right? I'm just, out of those 15 students, I'm choosing, and that's the key word, 5 people from a group of 15. So how would I write that out? I would write that out as 15C5, right? And again, if you have the button on the calculator, just punch it in your calculator. So 15C5, but it's probably a good idea to get in the habit of writing it out. So 15C5 really means 15P5 divided by 5 factorial. Because what the idea is, if you do 15P5, it's a permutation where the order matters, and the reason you're dividing by 5 factorial is you're dividing out all the duplicates, basically, is what it comes down to. You have to divide out all the ones that are duplicates. And I think we had talked about that briefly in our online meeting when I was talking about the card hands, right? Because like if you have an ace and a king, it's the same as a king and an ace. The order didn't matter, so you had to divide by 2. So here you're actually dividing by 5 factorial because there's a lot more duplicate groups that you'd get. But again, I mean, not super important to remember that. It's just, that's what you're doing. You're dividing out the duplicates. So 15P5 is 15 times 14 times 13 times 12 times 11, and 5 factorial is 5 times 4 times 3 times 2 times 1. So it is a lot easier, especially when you're doing the combinations, to just use the calculator button, right? So 15 C5. So I could choose 3003 distinct groups, right? So 3003. And again, that's only using 5 of the people. That's not breaking the whole class into groups. That's just taking 5 people from the 15 and making a group. All right. So, and then again, the same thing with the pizza toppings. It doesn't matter the order that you're doing. So if I'm choosing 3 toppings out of 9 possibilities, that's actually going to be 9C3 And 9C3 is going to be 9 times 8 times 7, right? It's 9P3 divided by 3 factorial, divided by 3 times 2 times 1. Okay, so 9C3, and if you have a scientific calculator and not a graphing calculator, there's probably a PRB button on the calculator. You don't have to go to a math menu. You probably just hit the PRB button. So that's 84. So 9C3 is 84. So there's 84 possible 3-topping pizzas that you can create. And then again, the thing to remember is, I keep stressing this, there was nothing special about the positions in the group. It doesn't matter which toppings get put on the pizza, first, second, or third. So that's why those problems are combinations and not permutations, right? Nothing special about the positions. And doesn't matter which topping gets put on the pizza, first, second, or third, right? Order was not important. So those were combinations.